Greetings, salutations, all those nice things. Welcome to lesson 2.7. It's me, Miss Thibodeau. No, I'm just kidding. I am not Miss Thibodeau. I'm Mr. Athide, and I'm coming in to assist. Miss Thibodeau's nearby. Give him a wave, Miss T. You can't see her, but she's definitely waving, and you should wave back. She'll feel it. All right, serious mode, math. We are combining exponent laws. You've used a bunch of exponent laws already. You know how to multiply some powers with the same base, or how to divide some powers with the same base, or to take some base to some power, to some exponent, and then raise that to another exponent, have a power of a power. In all cases, remember, exponent laws only apply to powers with the same base. So if we've got different bases, there are no power laws we can use to combine them. It'll be important for us to kind of establish common bases if we have numerical values that could be represented that way. When we are simplifying these expressions, some of them will have fractions involved, and it's a really good idea to treat the numerator as its own thing, maybe even put some giant brackets around it, and the denominator is its own thing. We can put some giant brackets around that too, but we can look at them separately before we simplify across that fraction line. The order of operations totally still applies, so that absolutely has to be respected in any operation that we do in math. And these exponent laws that we have, they apply to multiplication and division. And that's because exponents themselves are based on repeated multiplication. So exponent laws do not apply to addition and subtraction. When we're distributing a negative inside a set of brackets, remember, a negative is like multiplying by -1. So if we see something like -2 to the power of 5 to the power of 3, it's like taking that power of 3 and saying it applies to the -1 in front as well as the 2 to the 5. So we can kind of play with it that way. And it's a really good idea because that really gets at the idea as to where that negative applies. Is the whole thing going to be positive? Is it going to be negative? By making sure we're treating it as its own separate factor. So in these examples on this first page, we're going to simplify each expression and state your final answer in exponential form. This exponential form is kind of a hint that we are using some power laws. And simplify means make it as condensed as possible. We're going to perform every operation we can pretty much here. Looking at example A, there's a fraction involved, there's a numerator, there's a denominator. And the numerator has a few things happening. We've got an x to the 14, it's multiplying x squared, and it's multiplying x cubed. And we know that's multiplication because when there's no symbol in between terms, well, then it must be one giant product. So we know for sure that's what's going on here. Well, just say for a second, I've forgotten my exponent laws, and I have no idea what's going on, but I do know what an exponent is. I could take something like this and rewrite it just with all of that multiplication done. 6, 7, 8, 9, 10, 11, 12, 13, 14. There's x to the 14 right here. And that's getting multiplied by x squared, which is x times x. And that's getting multiplied by x cubed. X squared and x cubed. And that is a way for me to figure out what's happening. That's just a whole bunch of multiplication. Yeah, there's a whole bunch of multiplication to get through x to the 14, but then also more multiplication. This is just x being used as a factor however many times we've written it there. And the number of times we've written it is 14 right here, plus these 2, plus these 3. That's 19 times that we've written down x. As a result, even if we forget our power laws, we can say that that numerator is x to the power of 19. Our fast way of getting that is saying we're multiplying a bunch of powers with the same base. So we're going to keep the base and add the exponents together to give our new exponent. That's just the numerator. The denominator, nothing was done there, so that's still x to the power of 5. And now we have a quotient of powers. Quotient meaning that we're talking about division. This is x to the power of 19 divided by x to the power of 5. And our quotient law says that we must subtract the exponents. And remember, that's because if we did have a whole bunch of these up here, if we had 19 x's on top, that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And we had 5 x's on the bottom. Because division cancels out multiplication, it undoes it. Every division by x would cancel out a multiplication by x. So one of those x's would cancel one out. Another one on the bottom would cancel another on the top. That's 3. That's 4. That's 5. We took away 5 of the x's from the top. 5 are gone from the numerator. And that's why we are subtracting the exponents. So our result would be x to the power of whatever 19 minus 5 is. And these days, that is 14. This is as simplified as that can get. And it is in an exponential form because we can see the power. Next example, we're going to proceed with this one as well. Remember, BEDMAS still applies. When we look at this, you might be tempted to look at 2 to the power of 3 and say, oh, I know that's 2 times 2 times 2, that's 8, and write it down that way. Thing is, that wouldn't be in exponential form. It's a good idea to keep that written as 2 to the power of 3, because then we can start applying our power laws to it. Like when we have this power of 5, that's going to kind of distribute into everything. As well as this 2, whatever exponent's going to have on the bottom, we're going to be able to use our quotient law. So keep it in exponential form. All right, first thing I'm going to do is note we've got a power of a power. This power of 5, this exponent of 5, applies to everything in these brackets. Oh gosh, what have I done? Yeah, don't worry, I'll get back to the right page eventually. Nailed it, first try. All right. That power of 5, that exponent of 5 applies to everything in that numerator. So on top, that applies to this b squared. So that's b squared to the power of 5. We multiply the exponents. Why? Because that's like b squared times b squared times b squared times b squared times b squared. So 2 plus 2 plus 2 plus 2 plus 2. No, that's just 2 times 5. Wow, I could have just multiplied, which we did. A to the power of 4 to the power of 5. Well, that'll be a to the power of 20. And then we've got this negative 2 to the power of 3. But remember, we're treating that negative as if it's multiplying 2 to the power of 3 by negative 1. Order of operations says the 3 applies to the 2 first. That negative 1 is separate, so we're treating them as separate factors. So 2 to the power of 3 to the power of 5, that's 2 to the power of 15. And then negative 1 is to the power of 5. and that is the whole numerator. The denominator, there's some stuff going on there as well. Let's just move this a little bit out of the way. Oh gosh, what have I done? I tried. Undo that. Denominator, am I right? Yep, that's what I was doing this whole time. We've got 2a cubed b all to the power of 3. So that exponent of 3 applies to everything in there. You've got 2 to the power of 3. There's a cubed to the power of 3. 3 times 3 tells us the exponent is 9. And then b is also to the power of 3. I've done everything I can in the numerator. I've done everything I can in the denominator. Last thing to do will be apply the power rules to each one of these quotients. Overall, this whole thing's going to be negative because -1 to the power of 5 is negative. And that's kind of why we keep that negative on its own. So a big old negative marker. Then we've got 2 to the 15 divided by 2 cubed. Our quotient rule says that we subtract those exponents while keeping the base the same. So that's 2 to the power of 12. We've got a to the power of 20 divided by a to the power of 9, which will give us a to the power of 20 minus 9. That's 11. And then finally, b to the power of 10 divided by b to the power of 3. So b to the power of, well, 10 minus 3 is 7. And that one is DUN, done, done, done. Take a quick moment and give a try for these next few examples. If you're unsure, that's okay. Just go as far as you possibly can. And then we'll resume the video in a couple minutes and see what we all got. So pause now. And return now. So welcome back. Hopefully you've given these a try. Let's get into this and see what we can do. Example C. Oh boy, that's a lot of brackets. But that's stuff we can handle. There's a bunch of ways we could handle this. My recommendation is always go as far deep inside these brackets as you possibly can and evaluate or simplify from there. Ooh, one thing I'm noticing is an 81 and a 27. That might be a little scary to multiply, but I think those are both powers with a base of 3. So I could, first of all, I'm going to write the most outside brackets as square brackets. It just helps me with my own organization. But I'm going to rewrite that 81 as 3 to the power of something. 3 to the power of 1 is 3. So 3 squared is 9. 3 cubed is 9 times 3. That's 27. 3 to the 4 is 27 times 3. That's 81. Sure enough. All right, we're good here. I'm going to use that. So 81 is 3 to the 4. And we've got a squared b cubed. And then 27 I've also got over here. So 27 is 3 cubed. And then we've also got the a squared b to the 4 there. Close off my mega square bracket. And there's still that exponent of 2 outside. So when we go line to line here, we should be able to see what matches with what. So I've still got these a squareds, still got these b cubes, these a squareds, these b to the 4s, this exponent of 2 outside. Those are all same. The only thing that's changed is turning this 81 into 3 to the 4. There's that matchup, and 27 into 3 cubed. So we should always be able to see what matches with what. In my next line, I'm going to go inside those square brackets and say, hey, we're multiplying. We're multiplying a couple expressions that have powers, and those powers have a lot of same bases. So 3 to the 4 times 3 cubed. I'll be simplifying that. A squared times a squared. Be simplifying that. And b cubed times b to the 4. I'll be simplifying that. 3 to the 4 times 3 to the 3. We're going to add those powers together, or add those exponents together, and get 3 to the 7. A to the power of 2 times a to the power of 2. 2 plus 2 is 4. B to the power of 3 and b to the power of 4 being multiplied, and that gives us b to the power of 7. And I've still got that exponent of 2 way outside. And now we can apply that. So power of a power rule comes into play. So 3 to the power of 7 to the power of 2 is 3 to the power of 7 times 2, which is 14. A to the power of 4 to the power of 2 is a to the power of 4 times 2, which is 8. And then b to the power of 7 to the power of 2 is b to the power of 7 times 2. So that's 14. And this one is done. Worth noting, if we hadn't turned this 81, this 27 into powers of 3, we'd be working with whatever 81 times 27 is, which last I checked, is a pretty big number. And when we take 2187 to the power of 2, 2187 times 2187, that's getting a little absurd. If the numbers start becoming extremely unmanageable, it's probably a good idea for us to take a step back and just look at what we were actually dealing with and see if there's a better approach that we could work with, like in that case. But also because this question said, hey, put these things in exponential form, really we should be involving exponents for any of those numbery parts we see. All right, next example. I've got some stuff in a numerator, I've got some stuff in a denominator. I'm going to see what I can combine. The denominator looks a-okay as it is, so I'll leave that. M to the 4, P to the 9, Q. And then on top, a product, multiplying these two sets of brackets together. M to the 8 times M to the 3 is M to the 11 from adding those exponents together. N to the 5 doesn't have anything to multiply by. Poor thing, it's on its own. It's all right, N to the 5. And then P to the 2 times P to the 7. That will have us keep the P as the base, and the exponent is 2 times 7. That's a 9. In our next step, some things will cancel. We've got probably a fraction still. I'm thinking that just because this Q's over here on the bottom, and there's nothing for it to play with on top. Very sad for Q. Not sad for us, because we know how to handle that. So that Q is just going to be left there. But the other things, we've got M to the 11 on top, and that's being divided by M to the 4. So quotient of powers says we're subtracting those exponents. M to the 7. N had nothing to combine with, so it's just on its own. Good job, N. You keep doing your thing. And then P to the 9 divided by P to the 9. Whoa! Those are the same numbers. Bunch of ways of looking at this. One is noting, hey, they're the exact same thing, so they cancel each other out. What do they cancel each other out to? Well, that would be a 1. So division causes cancellation to 1. But we don't really write multiplication by 1. The other way to look at that would be to say, hey, 9 minus 9 is 0. but anything to the power of 0 is 1. So again, we should leave that in the best form, not really written in. And there's our final answer. Example E. Whoa! It's a lot of zeros. It's all right. This is all super manageable because if I see a 1 followed by a bunch of zeros, it's got to be 10 to the power of something. Okay, there's some division and some multiplication going on. But let's just figure out these powers of 10. This first thing here is 10 to the power of, I'm going to count the zeros, that's 1, 2, 3, 4, 5, 6 of them. So this is 10 to the power of 6. Still have a to the 8, still have b to the 9. We're dividing by 10,000, and that's a 1 followed by 4 zeros, so that's 10 to the power of 4. You've got a to the 5, b to the 5, and then this is getting multiplied by ab squared. Neat. Remember, when we have multiplication and division in the same line, we should be tackling them in order as they appear left to right. This division appears before this multiplication in this one line that we see. So that's what we're starting with, that division. 10 to the power of 6 divided by 10 to the power of 4 is something with a base of 10 and exponent of 6 minus 4, so 2. A to the power of 8 divided by a to the power of 5 will give us something with a base of 8 and an exponent of 8 minus 5, so that's 3. And then b to the power of 9 divided by b to the power of 5 gives us a base of b and an exponent of 9 minus 5, which is 4. That's that division handled. We still have this times ab squared at the end there. So that still gets written in. And now we have a product. There's nothing for the 10 squared to multiply with, so it's just kicking about on its own. Oh, sorry, this Apple Pencil got loose. There we go. 10 squared. We've got a cubed times a. And, oh, I don't see an exponent on that a. Is that a 0? No, it's not. Remember, the invisible exponent is a 1. So a cubed times a to the 1 is a to the 4. And then b to the 4 times b to the power of 2 is b to the power of 6. So we just added a bunch of exponents. Cool beans. If you got that, give yourself a way high five. That should be way above your head. On the next page, we have another example. So this page, we were just doing a bunch of simplification. On the next page, we are tasked with evaluating each expression. And to evaluate is to find the value of. And we want to be able to write something as just a straight up number, not something with powers involved, preferably not something with multiplication or division involved, just a straight up, here's the number we're dealing with kind of situation. To get there, we might want to use our power laws. If we didn't and we started saying, okay, let's figure out what 3 to the 5 is, and we said 3 times 3 times 3 times 3 times 3, and we evaluated that, so like this is 9, and that's 9, and this is 3, and then that's 81 times 3, and we got 243, but then that's multiplied by 3 to the power of 1. The numbers, they're getting out of hand. I can't handle all these numbers. Power laws can really make this simplification part easier. So we're going to simplify as much as we can and then evaluate. So using the same rules as on the previous page, I'm looking at this numerator, seeing I've got some powers that have the same base, and saying, well, if I'm multiplying powers with the same base, I'm just going to keep that base and add the exponents. So 3 to the 5 times 3 to the 1 is 3 to the 6. And the bottom is just 3 cubed. There's nothing else happening on the bottom of that fraction. That denominator is just doing its thing. Now I've got 3 to the power of 6 divided by 3 to the power of 3. That's a quotient of powers. So I'm going to keep that base, subtract the exponent. 6 minus 3 is 3. And now I'm just dealing with a single power, not a product and quotient of powers, just one little power to evaluate. And we can get 3 to the power of 3. Maybe you've memorized it. You know exactly what the answer is. Maybe you're unsure, and that's okay. So you're going to your scrap work and you're saying, well, not 2. 3 times 3 times 3 is something. 3 times 3. I swear that other number is a 3. 3 times 3 is 9. So 3 times 3 times 3 would be 9 times 3. So 27. Ideally, through repetition, that's one that's going to stick in your memory. But if not, there's always a way for us to get it. I dare you to take a quick pause and try this other one. Play around with the power laws we're using. Simplify it as much as you can. And then see if you can get a value out of it. So quick pause now. Whoa, you resumed. Welcome back. Let's tackle this thing. There's a lot of powers of 2. There's a lot of powers of 5. We're going to simplify as much as we can. That numerator could use a bit of work. Denominator, you're doing great. Keep it up, denominator. Numerator? What is happening? Here's 2's and 5's all over the place. We've got 2 to the 4 times 5 to the 3 times 2 to the 3 times 5 to the 6. It's just multiplication all throughout. So power laws apply. 2 to the 4 times 2 to the 3 will give us a base of 2 and an exponent of 4 plus 3 is 7. Don't mind me as I figure out how to write 7. Nailed it. And then we've got 5 to the power of 3 times 5 to the power of 6, which will give us a base of 5 and an exponent of 3 plus 6, which is 9. Our next step, well, now we've just got some quotients to deal with. These powers of 2 will line up. These powers of 5 will line up. So we'll play with them each separately. 2 to the power of 7 divided by 2 to the power of 2. Quotient of powers says we'll keep that base and subtract the exponents to give us 2 to the power of 5. And then 5 to the power of 9 divided by 5 to the power of 5. Keep that base, subtract those exponents. So this is now in a pretty good condensed form. It looks way simpler than what we started with. We haven't finished. This is in an exponential form. And remember, the task said evaluate. So we need to finish off with just a straight up number here. Bunch of ways we can do this. If you figure out what 2 times 2 times 2 times 2 times 2 is, that would be 32. And 5 times 5 times 5 times 5, that 5 to the 4, 5 times 5 times 5 times 5 is like 25 times 25. And whether you know this already off the top of your head or not, 5 times 5 times 5 times 5, which is 25 times 25, is 625. It's another one worth committing to memory if you've got the memory space for it. And now we need to figure out what 32 times 625 is. Any kind of multiplication method can be your friend. I'm a long multiplication person myself. So 2 times 5 is 10. 2 times 2 is 4, with that 5. And then 2 times 6 is 12. Placeholder 0 for the tens, or for the ones, I should say. 3 times 5 is 15. Carry that 1 up. 3 times 2 is 6. So plus 1 is 7. 3 times 6 is 18. And adding 0 plus 0 is 0. 5 plus 5 is 10. Carry that one. 2 plus 7 plus 1 is 10. Carry that one up. 1 plus 1 plus 8 is 10. Carry that one up. All right, I got myself a 20,000. 20,000. There's another way to get this. I really love it when 2s and 5s are getting multiplied, mainly because I know that 2 times 5 is 10. So if you want to play with this a different way, and if you happen to see that you've got 2s and 5s being multiplied, you can actually write this a different way. And if you want, like, you can just start tuning out. You don't have to listen to the rest of what I'm saying right now. But if you're interested in math, which you should be, this could be really exciting. 2 to the power of 5 is 2 times 2 times 2 times 2 times 2. 5 to the 4 is 5 times 5 times 5 times 5. And we could rewrite this if we wanted to have all these 2s and 5s grouped together, at least in our head brain. Every pair of 2 times 5 would give us a 10. So this 2 times 5 gives us a 10. This 2 times 5 gives us a 10. This 2 times 5 gives us a 10. And this 2 times 5 also gives us a 10. And we still have that 1, 2 kicking around. So really, we've got 2 times these 4 10s. That first 10, that second 10, that third 10, that fourth 10. And that's pretty wicked easy to multiply, because to multiply by 10 just means shift the decimal place over, or if you don't see one, just throw a 0 on. So the first 10, the second 10, the third 10, the fourth 10. Whoa! That's way easier, at least to me. So to each their own. You'll have to choose the method that works best for you. Regardless, the answer to this is 20,000, and that's the number you need to end up with at the end. You're right, I should put a nice box around that to say final answer attained. Make it real clear for the reader. All right, well, that is all that. I'm sure there's some practice work for you to work on, so I strongly suggest working on it. If you have questions or comments or concerns, you know what to do. Message your teacher person, come to Extra Help. There's all sorts of opportunities. This has been most lovely. I hope you found it entertaining. And remember, you've got the power.